2 watts. That's less electricity than an old phone charger wasting power in a wall socket overnight. Less than many LED light bulbs. And according to researchers tied to China's National University of Defense Technology, it's enough to run an AI-oriented military chip architecture the Pentagon currently doesn't appear to have an equivalent for in public development. That sentence should sound wrong. Modern AI systems inhale electricity. Nvidia's H100 chips can pull 700 watts under load. Data centers are now being designed next to nuclear reactors because training large models is starting to resemble heavy industry more than software. Yet, here's China publishing papers about ultra-low-power battlefield AI systems designed to operate in environments where electricity, cooling, and communications may barely exist at all, which changes the conversation completely. Because most people still think the AI race is about who has the biggest data center. Bigger clusters, bigger models, bigger budgets. Silicon Valley thinking, basically. But militaries don't fight wars inside climate-controlled server racks outside Phoenix, Arizona. They fight in deserts, mountains, oceans, damaged cities, electronic warfare zones. Places where heat gets you killed and battery logistics become strategy. That's the part Washington may be underestimating. In 2022, the United States launched the most aggressive semiconductor restrictions in modern history. The Commerce Department's Bureau of Industry and Security cut China off from advanced lithography equipment, high-end AI GPUs, and critical manufacturing tools. The assumption underneath the policy was fairly simple. Advanced computing equals advanced warfare. Therefore, restrict computing. Reasonable logic. Except China appears to have adapted sideways instead of directly. Rather than matching Nvidia chip for chip at hyperscale AI, parts of China's defense research ecosystem started focusing on efficiency per watt. Tiny autonomous systems, distributed edge computing, neuromorphic architectures inspired by the human brain, AI that can survive without cloud infrastructure because the cloud may not exist in an actual war between peer states. A little dry humor here. America sanctioned China's access to massive AI accelerators. China's response seems to have been, fine, we'll make the machine smaller and teach it to sip electricity instead. And honestly, that may matter more. Think about what modern militaries are quietly running into right now. Drone swarms drain batteries fast. Portable radar systems overheat. Autonomous underwater vehicles have endurance limits. Soldiers already carry absurd amounts of weight. Communications gear, optics, thermal systems, power packs. The U.S. Army has been worrying about battlefield energy logistics for over a decade. RAND reports and DARPA projects keep circling the same problem from different angles. Modern warfare increasingly depends on mobile electricity. Not fuel alone, electricity. There's a reason the Pentagon's Replicator initiative suddenly became urgent in 2023. Cheap autonomous systems are changing the math of deterrence. Ukraine exposed part of this reality already. Expensive platforms can be harassed, tracked, or exhausted by relatively cheap unmanned systems produced at industrial scale. But here's the uncomfortable technical wrinkle buried underneath all this. Autonomous systems become dramatically more dangerous when they no longer need constant communication with centralized servers. If AI processing happens locally, on-device, low-power, hardened against jamming, then destroying communications infrastructure stops being enough. The drone still thinks. The sensor still classifies targets. The missile still adapts mid-flight. And this is where that 2-watt figure starts becoming less absurd and more strategic. I'm not fully convinced China has solved this at operational scale yet. There's a huge difference between laboratory papers and deployable military systems. The Pentagon knows that better than anyone. American defense history is filled with prototypes that looked revolutionary until reality arrived carrying mud, heat, and budget overruns. Still, something about this trend feels bigger than one chip announcement, because the deeper story may not be about semiconductors at all. It may be about a military doctrine quietly shifting towards systems designed to survive scarcity rather than abundance. And the country most prepared for that world may not be the one people assume. The strange thing is that China's military AI push stopped looking like Silicon Valley years ago. That matters more than people realize. American tech culture still assumes computing power scales upward through concentration. Giant server farms, giant capital expenditure, giant cooling systems. Even the language sounds industrial. Clusters, foundries, megawatts. Meanwhile, Chinese military researchers, particularly teams connected to the PLA's Academy of Military Sciences and the National University of Defense Technology in Changsha, increasingly write about distributed intelligence, edge autonomy, and cognitive resilience under contested conditions. Those phrases sound academic until you translate them into battlefield terms. It means systems designed to keep functioning after satellites fail, communications are jammed, and logistics chains fracture. That's a very different philosophy, and there's historical logic behind it. China watched American wars for 30 years: Iraq, Kosovo, Afghanistan, Libya. The opening phase was usually the same. The US achieved information dominance first. Blind the enemy, control the spectrum, centralize command, then dismantle resistance piece by piece using overwhelming coordination. So if you're Beijing studying how to survive a conflict against the United States, you naturally start asking a different question. What happens when coordination disappears? That's where low-power AI becomes strategically interesting. Take unmanned naval systems, for example. The South China Sea is enormous. Constant communication across thousands of kilometers becomes vulnerable during wartime. Satellite links can be disrupted. Radio emissions reveal position. Yet autonomous maritime drones still need navigation, target recognition, and decision-making capability. Running those functions locally with minimal power draw changes endurance dramatically. A drone that processes onboard instead of constantly transmitting data home doesn't just save electricity. It becomes harder to detect. Small detail, big implication. The same principle applies to infantry systems. The U.S. Army's next-generation squad weapon program already ran into concerns about battery burden because modern soldiers increasingly resemble walking electronics platforms. Thermal sights, network radios, augmented targeting systems, navigation units. It adds up fast. In Afghanistan, some patrols reportedly carried over 20 pounds of batteries alone, depending on mission length. 20 pounds. That's not a software problem anymore. That's biomechanics. Meanwhile, Chinese defense journals have spent years discussing neuromorphic computing, chips designed to mimic neural structures in the brain. Instead of brute force processing, these architectures prioritize event-based computation and energy efficiency. Intel experimented with this too through its Loihe research chip, but China appears unusually focused on military application under constrained environments. And here's where the conversation gets awkward for Washington, because the United States still dominates frontier semiconductor technology overall. TSMC remains unmatched at scale manufacturing. Nvidia still owns the AI accelerator market. ASML's EUV lithography machines remain critical choke points. On paper, America and its allies retain the high ground, but battlefield advantage isn't always built from the highest performing technology. Sometimes it comes from the technology that survives longest under pressure. The Soviet T-34 tank wasn't the most sophisticated armored vehicle of World War II. It was rugged, scalable, and brutally practical. Military history keeps repeating this lesson in different forms. Elegant systems often struggle when maintenance collapses or supply chains stretch thin. There's a reason DARPA itself keeps funding low-power AI initiatives. The Pentagon understands the vulnerability. The issue is speed. Defense procurement cycles move slowly. China's military-civil fusion system does not. That phrase gets tossed around casually, but it's worth understanding what it actually means. Since around 2015, Beijing has systematically pushed universities, private firms, semiconductor labs, and defense institutions into overlapping ecosystems where discoveries transfer faster between civilian and military sectors. Not perfectly, not frictionlessly, but faster than many Western systems built around stricter separation. The result is messy, difficult to track, and occasionally inefficient. It's also capable of moving very quickly once leadership priorities align. And right now, energy-efficient AI appears to be one of those priorities. What keeps nagging at me is the timing. China accelerated this push after sanctions intensified, not before, which suggests something important psychologically. Beijing may no longer believe catching America directly is realistic in every category simultaneously. Instead, it's searching for areas where constraints themselves become weapons. Less power consumption, less heat, less dependency, less to target. We'll come back to that idea later because it connects to something much larger happening inside modern military planning, something the public discussion around AI still barely touches. There's another reason the 2-watt claim matters: heat. Not processing power, not transistor counts, heat. Modern military systems are becoming thermal nightmares. High-performance chips generate enormous amounts of it, and on a battlefield, heat is basically a broadcast signal announcing your location to anyone with modern infrared surveillance. That changes design priorities in ways civilians rarely think about. A fighter jet can hide emissions briefly. A submarine can reduce acoustic signatures. But electronics always leak something, especially powerful ones, and that creates a strange reversal in the AI arms race. For the past few years, public conversation has treated larger models as inherently superior. Bigger parameter counts, bigger compute budgets, bigger energy consumption. OpenAI, Google, Anthropic, the commercial sector normalized the idea that scaling laws solve everything if you throw enough silicon and electricity at them. Military systems don't necessarily reward that logic. A battlefield AI doesn't need to write poetry or generate photorealistic cats wearing medieval armor. It needs to identify objects, adapt to terrain, classify threats, and continue functioning after communications degrade. Different problem. Different optimization curve, which means the winner may not be whoever builds the smartest system. It may be whoever builds the smartest acceptable system that can survive under stress. That distinction matters enormously. Look at what's happening in drone warfare already. In Ukraine, FPV drones costing a few $100s are forcing both sides to rethink armored warfare doctrines developed over decades. Expensive tanks increasingly operate under constant surveillance from cheap airborne systems assembled with commercial electronics. Some units reportedly cycle through drones almost like artillery ammunition now. Quantity is becoming intelligence by accumulation, but those systems still depend heavily on human operators and communication links. Jam the signal, and effectiveness drops sharply. The obvious next step is greater onboard autonomy. Not Hollywood-style killer robots wandering independently through cities. More mundane than that. Target tracking, navigation adjustment, threat recognition, localized tactical decisions made without waiting for remote instructions. And that requires efficient edge computing. This is where I think people sometimes misunderstand China's strategic culture. Western commentary often swings between two extremes. Either China is technologically unstoppable, or it's permanently years behind. Reality is more irritatingly complicated. China's system is uneven. Some sectors are world-class. Others are inflated by subsidies and political incentives. Certain state-backed semiconductor projects collapsed spectacularly after burning billions of yuan. Beijing has its own bureaucratic dysfunction. Plenty of it. But the broader trajectory still matters, especially because China appears willing to pursue approaches Western firms often consider commercially unattractive. Neuromorphic computing is a good example. For consumer markets, these architectures remain niche and difficult to monetize. For military systems operating under severe energy constraints, they suddenly make more sense. That's not accidental. In 2024, Chinese researchers published multiple papers exploring spiking neural networks and low-power inference architectures specifically for autonomous platforms. Some referenced energy reductions large enough to extend operational endurance meaningfully in small unmanned systems. Again, laboratory conditions are not battlefield reality. Important caveat. Still, notice the pattern. America dominates centralized AI infrastructure. China increasingly experiments with decentralized survivability. Different assumptions about the future. And honestly, I suspect this divergence reflects geography as much as technology. The United States historically fights expeditionary wars, supported by global logistics networks. China's military planning focuses heavily on contested regional conflict near its own coastline, where communications disruption and saturation attacks become far more likely. That changes engineering incentives. Here's the deeper issue hiding underneath all this. Advanced warfare may be approaching an energy wall. Every new sensor, autonomous platform, communication node, and AI process increases power demand. Yet batteries improve slowly compared to computing requirements. Physics eventually starts arguing back, quietly at first, then all at once. Which brings us back to that tiny number from the opening, 2 watts. The figure sounded unimpressive because consumer technology trained us to equate power consumption with capability. More watts meant more performance. Bigger GPU, bigger server, bigger everything. Military systems don't always obey consumer logic. Sometimes the most dangerous machine in the room is the one that barely needs electricity at all. And if China is genuinely building doctrine around that reality before the Pentagon fully adapts to it, then this story stops being about semiconductors. It becomes a story about which country correctly understood the limits of the next era first. Remember that number from the opening, 2 watts. What makes it unsettling isn't the engineering achievement by itself. It's what the number implies about the direction modern warfare may already be moving. Because if the future battlefield rewards endurance over raw performance, then decades of assumptions about military superiority start looking less stable. The United States built an extraordinary war machine around abundance. Abundant carrier strike groups, abundant satellite coverage, abundant logistics capacity, abundant compute power. And to be clear, that system remains terrifyingly capable. Anyone pretending American military technology suddenly became obsolete is selling ideology, not analysis. But abundance creates habits. You optimize around access to fuel, cooling, bandwidth, secure communications, replacement parts. You assume systems can constantly synchronize with larger networks because, historically, they could. China, by contrast, increasingly appears to be preparing for environments where many of those assumptions collapse early. Not because Beijing expects technological superiority across the board, because it expects disruption. That's a different mindset entirely. And honestly, some of this is already visible outside the military sphere. China's commercial technology ecosystem became unusually good at optimization under constraint long before the semiconductor sanctions hit. WeChat integrated half the internet into one app, partly because Chinese smartphone hardware historically lagged behind flagship Western devices. BYD became aggressive about battery efficiency because energy economics mattered more in China's domestic market. Huawei learned to survive sanctions by redesigning supply chains under pressure, rather than waiting for pressure to disappear. Constraint became institutional muscle memory. That doesn't automatically translate into military victory. Important distinction. Wars are decided by production capacity, alliances, geography, training, morale, intelligence quality, political leadership, usually all at once. Technology alone rarely delivers clean outcomes, despite how defense contractors market things. Still, I think Washington may be underestimating how quickly the definition of advanced is shifting. The Pentagon still spends enormous amounts preparing for high-end conventional dominance. Hypersonics, 6th-generation fighters, massive AI cloud integration, all rational priorities. But future conflict may also reward systems that are cheap, autonomous, low signature, power efficient, and impossible to fully disable because they don't rely on centralized infrastructure in the first place. That's a harder problem. You can destroy an airfield, you can jam a satellite link, you can target a data center. But what happens when intelligence is dispersed across thousands of tiny devices, operating semi-independently with minimal energy requirements? The economics of defense start bending in uncomfortable ways. There's also a psychological component here people don't discuss enough. American strategic culture often assumes sanctions preserve technological distance indefinitely. Sometimes they do. The restrictions on advanced lithography genuinely hurt China. Losing access to ASML's EUV machines was not a minor inconvenience. But sanctions can also force adaptation patterns that produce unexpected results later. Japan learned manufacturing efficiency after resource scarcity. The Soviet space program became extraordinarily weight-conscious because launch capability was constrained. Huawei reportedly pushed aggressively into chip packaging innovation after losing access to leading-edge fabrication. Pressure changes engineering priorities, occasionally for the better. My own view is that China still trails the United States and frontier AI infrastructure overall. I don't think that gap disappears soon. Nvidia's ecosystem advantage is real. America's research universities remain unmatched collectively. The alliance network around semiconductors, Taiwan, Japan, South Korea, the Netherlands, still gives Washington structural leverage Beijing would love to break. But I also think the public conversation is focused on the wrong scoreboard. The next military revolution may not belong to the country with the largest AI model. It may belong to the country that figured out how to make intelligence cheap, mobile, heat-resistant, and nearly impossible to switch off. And if that's true, then historians may eventually look back at these tiny, low-power chips the same way they looked at early radar systems before World War II. Not impressive to the public at first glance, but quietly rewriting the logic underneath conflict, which is probably why the Pentagon is paying attention now, even if it isn't saying much publicly. Because once military competition turns into an energy efficiency race, the assumptions get uncomfortable very quickly, especially for countries accustomed to unlimited power. If you enjoyed this one, stick around. There are a few more technologies hiding in plain sight right now that deserve a much closer look.